Hello, good evening. Let's get started with a quick review of the previous week's session. In the last week, we started discussing about multi-objective optimization, and then we also gave a brief idea about two different approaches used for this particular technique. One being the preference-based method, where the primary idea is to convert your multi-objective optimization problem into a single objective optimization problem. This is essentially done using some high-level information, where you define a new function. The fundamental idea in the preference-based approach as we have seen previously, say if you have functions, objective functions such as minimize f1, f2, so on, say you have m objective functions. Now we kind of formulate the problem in a different way, where we define a new function capital F of x, which is a weight combination of all these objective functions. Where m equal to 1, it ranges till the number of objective functions. So this is the one we have considered previously. And then we also discussed about something called ideal optimization approach, where we kind of identify all the possible optimal solutions. This is something we do with the evolutionary computation techniques. The main principles of this multi-object optimization lies in obtaining the Pareto optimal solutions. We have discussed that over the last week. These Pareto optimal solutions are basically the ones which are non-dominated. In a sense, when you have two solutions which belong to the Pareto optimal set, you cannot say which one of them is better than the other. The example which we considered previously includes, say, you have the objective function values f1 and f2 as 0.1, 0.3. This is for one individual. And for the second individual, say you have another values of, say, 0.2 and 0.4. When you want to compare these two solutions, solution 1 and solution 2, you can clearly see like solution 1 is better than solution 1, the value of f1 for solution 1, and you want to compare with the value of f1 for solution 2. Similarly, if you want to compare the value of f2 for solution 1 and f2 for solution 2, in the first case, f1 for solution 1 and f1 for solution 2, clearly 1 is less than 2. And even in the second case, if you happen to see this particular context, in this particular case, you can also come up with the same value saying f2 for 1 is less than 2. So clearly, you can see if your problem is the minimization problem, solution 1 actually dominates solution 2. This is what we discussed previously. Now, in the case of Pareto optimal solutions, you do not have the concept of dominance. You have something called non-dominated solutions. Say we'll consider another solution 3. Say 0.2 and 0.1. Now, when you want to compare 1 and 3 over here, you can see like for the f1 for solution 1, f1 for solution 1 is actually less than the value of objective 1 for solution 3, but when you want to compare f2 for solution 1 is actually greater than f2 for solution 3. So now among 1 and 3, you cannot say which one is better or worse than the other. So this is what we call non-dominated solutions.
What is this f1 dash?
This I'm saying f1 is essentially like for the first individual objective function value 1.
Okay.
f1(3) is basically for the third individual objective value of function 1. Okay.
Okay.
So in your objective space, out of all the functions, out of all the solutions when you get, the set of all such non-dominated solutions is what we are calling the Pareto solutions.
What are the dash values?
Dash value, sorry, I didn't get it. Which ones?
F2 prime, F1 prime.
No, they are not essentially primes. So this, I'm saying these are the individuals. The first individual,
Okay.
second individual.
Mm-hmm.
Maybe the notation might be complete. Now I hope it is clear.
Okay.
Okay. So when you are comparing two individuals, you check across all the objective functions and see whether all the objective functions of one is better than the other or not. Okay.
Mm-hmm.
So once we define the Pareto optimal solutions, the next step we discussed over the last week is essentially all these Pareto optimal solutions form a set, and the locus of all this is what we call the Pareto optimal front. And our objective in any of the algorithm, when we develop an algorithm, is essentially to converge our solutions to the Pareto optimal front. And we also discussed last time that when we converge to the Pareto optimal front, the solution should be diverse enough, in the sense that they should occupy the entire Pareto front. So if this is your objective space of, say, bi-objective, essentially two objective functions f2 and f1, and if it so happens that you want to minimize both the objective functions, and your Pareto front looks something like this. What we are saying is when you identify the solutions, they should be covering the entire Pareto front, and they should be diverse enough. Like this is what we are expecting the final solution of our algorithm should be. Unlike the one, say, you can also have a less diverse solution, which is something like if all your individuals in the population are something confined to one narrow area. This is what we are not expecting. We essentially want them to be spread across the entire Pareto front. That is our goal in whatever algorithm we are designing. It should satisfy this criteria.
All individuals on Pareto front will be non-dominated type.
Yes, like the set of all non-dominated solutions, with them you form the Pareto front. Like you can see in these solutions, say we give a names for each one of them. So if you want to say 1 and this is 2, you can see here for 1 and 2, if you follow the same notation, f1 of 1 is actually less than f1 for the second individual. But if you happen to see the value of f2 of 1 is actually greater than f2 of 2. So these points are essentially non-dominated.
If one
f1 of 1 is essentially this one.
yes, then F1 of 1.
This
Yes.
is f1 of 2. And this will
Yeah.
be your f2 of 1. And this will be your f2 of 2.
F1. Yes, yes.
Okay. So when you have such a set
So
of points.
today the background.
Sorry?
Excuse me.
Yeah.
Today that background is a gray color. So can you make it white?
Oh, you are saying it is not visible?
It is not that much clear.
Okay, once.
Compared to the white background. Yes, sir. Right.
Clear, right?
Yeah.
So this is my f1 of 1, and this particular point is f1 of 2. Similarly, this will be my f2 of 1, and this will be f2 of 2. So all the points on this particular front, whatever point you have considered, any 2 points, if you consider any pair of points, they'll essentially form a non-dominated set. So the locus of all of them will be your entire Pareto front. So our objective in any multi-objective optimization algorithm is essentially to obtain all the points on this Pareto front, basically to obtain this Pareto front.
Here, sir, you have taken both x and y axis, minimum of function f1 and minimum of f2. Suppose it is minimum
this
and
is
maximum.
not. Then the shape of the Pareto front will be different. Like I think last week we discussed regarding that. So, okay, sorry if this is in black. I hope this is visible.
Okay. So
When you are
both
having
minimum,
both are minimum, you will have your Pareto front somewhere over here. When you have max of one function, minimum of another function, then it will be somewhere over here.
Here it is a elliptical shape, and the tilt is you can say right side. Suppose tilt is opposite side, then how will it change?
I didn't get your question. Second. So you are
This
saying
ellipse, no? Ellipse you have shown.
In the ellipse I have shown. Yes.
The contour plot of this
this one.
Pareto fronts.
Yeah.
Yeah. So now it is like tilting this side. Suppose this is a 180-degree turn.
Okay. So you're saying instead if we have something like normal ellipse, something like this. Or maybe
no,
one second.
Just turn. Yeah.
Something like
right
this.
Side up. Right side up.
Right side up.
Right side up, sir.
Something like this.
Means tilted towards the right. Tilted towards right. Yes, sir. Yes, sir. Yes, sir.
Okay.
Suppose the shape is like this.
Okay. And your objective is essentially minimize or maximize?
You
want to maximize?
How will it change? See, earlier the shape was just opposite. The direction of ellipse was opposite, and here for same minimum and minimum, how Pareto front will move?
So you're saying both are minimum and minimum?
Minimum, yes.
Minimum, and your shape of your objective space is something like this. Then what is going to happen? Yeah, it will be similar.
Earlier you have given an example for when this ellipse was turning left side. Now it is turning right side.
Yeah, here also it will be same. So you can see here, like you want to minimize f2. So when you want to minimize f2, you should essentially be somewhere in this region, right? You want to minimize both the functions, so you should be somewhere in this region. So you can see, say if I consider 2 points, somewhere over some point here and say point number 2 here, this particular portion of whatever is there is dominated in the sense, say if you consider f1 and f2 for this particular point and an f1 and f2 for this particular point, clearly like let's put some names A and B. Point B is dominating point A, right? By dominating, I mean point B is better than point A. When you want to minimize both of them, what we will do is essentially you have you define an origin somewhere at the point of here. Let's say this is our origin. Pareto front will be like somewhere something that is directed towards the origin. So anything, if you join this particular point and this and this and this, so in this particular rectangular region, maybe 1 second, I'll just draw only one of them. When you have A and B, something like this. When I first want to highlight in this particular area for the point A, you see point B lies in that particular area.
Yes.
So which means B is dominating A. So it won't cover in that particular region that I have highlighted there. So it should be somewhere at the bottom side.
Okay.
Let me just draw that.
Yes.
My screen visible or is it frozen?
B is dominating A.
Yeah.
Here B is dominating A.
Yes.
So in such case, this Pareto front will be at the left corner. Now suppose x-axis is a maximum of f1, then how will it move?
1 second. I think my screen is not visible. Yeah, now it is. So you're saying, so if instead of minimization, if it is a maximization.
Yeah, x-axis, it is maximum of f1.
So you consider the same case. So you just consider some small region, consider 2 points somewhere over here.
Sir, please change the color, which is not visible. That
Yeah.
yellow is not visible.
1 second. Yeah, I'm keeping it blue. So you're
Blue
saying
or
if you
black,
want,
yeah, sir.
I'm actually
is,
using blue, but it's not showing up, I guess. 1 second, let me join again.
huh, huh.
Yeah, sorry, I just got disconnected.
Yes.
Yeah, now it's visible, right?
Yes, sir. Yes, sir.
Yeah, so you're saying you want to maximize F1 and at the same time minimize F2. So maximizing F1 and minimizing F2 should be somewhere along this line, like this particular portion.
Maximize f1 and okay, sir.
So if you consider one point over here and another point over here, let's say this is point A and point B. So for point A, F1 for point A, and you want to compare with F1 for point B. Similarly, F2 for point A, you want to compare with F2 for point B. So F1A is greater than F1B, and F2A is actually, this is also greater than F2B.
Yes.
And your idea is essentially you want to maximize F1. So the first condition is true.
Yeah.
But you want to minimize F2.
Yes.
So this shouldn't be the case, right?
Yeah, I think that lower side, it should be lower side.
Yeah, it should be lower sign. Only then they will be dominating each other. So which means this set of solutions are basically non-dominated. So your friend should be somewhere, should include these A and B points as well. So like A and B points should lie on the Pareto front. If you consider any point over here, say some C, if you want to compare B and C, they're also kind of non-dominated in way like for B, F1 is maximized and for C, F2 is minimized. So they're also non-dominated. So this entire region is essentially having set of non-dominated solutions.
So this AB will also lie on Pareto front?
Yeah, they're essentially non-dominating, right? You cannot say which one of them is better. Like if you want to say whether A is better or B is better.
But if I see C and D at the bottom,
C and
they
D
are better. At least they are satisfying a minimum of F2 compared to A and
yeah,
B.
they are satisfying minimum of F2, but your another objective is essentially to maximize F1, right? You essentially have two objectives. You want to minimize F2 and maximize F1. If you want to compare, say, A at the top and D at the bottom, for A, F2 and F1 both are high.
Mm.
For D, F2 is minimum, F1 is also minimum.
So it means
It
I
means they are
can
not
say
dominated. You cannot say which one of them is better.
then Pareto front will be from D to A.
Yes, this region.
Uh, Can you highlight, sir? Whole.
Clear?
Okay, sir.
Like the idea
In
is the
earlier,
simple. You essentially need to identify the points which are kind of
hmm.
non-dominated and join all of them, and then you get the Pareto front. We'll actually take up an
Okay.
example and actually draw how the Pareto front opts. Like we'll do it analytically.
Another condition, sir.
Yes.
When if I make it reverse,
You mean
maximum F2 and minimum F1. Yeah, minimum of F1, maximum F2.
so? It should be somewhere along the opposite end, right? Like it is just you just have flipped the x and y axis, so it would just shift to the other side. Like I mean, something like this.
Okay.
Like you just flipped x and y
Okay.
axis.
Okay, sir. And similarly, when both are maximum, then it will
Then
be at the top.
top, yeah, it will be somewhere along here, small part.
Okay, sir. Okay, okay. Got it, sir.
Okay. Yeah, last week we stopped at this particular point after defining the Pareto chord. Then we also discussed about how do we actually measure the dominance. So we discussed
Yes.
two methods of dominance rank. And we also discussed about dominance count, and then we also discussed
Oh.
about dominance depth. So these are essentially to measure these are some metrics to measure how each of these solutions can be saved when you have a set of solutions. Let me just show one.
Here, sir, please clear one doubt.
Yeah, yeah.
You have taken at x-axis minimum F1 and y-axis some minimum of F2,
Hmm.
and then you have taken for rank you have taken the rectangle,
Hmm.
horizontal and vertical down.
Yes.
Okay, but sometimes you have to take the vertical up.
Yeah. If your problem is the other way around, say if you have some solutions like this, so these are my two corners, and these are some solutions
Yeah.
in that objective space. So for any one point, when you
Yeah.
want to calculate rank, what we have done last time is, since we want to minimize both of them, this is my kind of an ideal position. We will define it later. You have something called ideal objective vector. We will come to it later. But basically what we are saying, when you want to minimize both of them, we will start from the left bottom corner. If you want to maximize
Yeah.
both of them, you start from the top right corner.
Mm-hmm.
Or depending on the case, if you want to maximize F2, minimize F1, then you will start somewhere from here, like on the left top. Or if you want to maximize F1 and minimize F2, depending on your
Please, please give one example each, just like this Pareto front you have explained how it
okay.
will shift. So that will be clear then.
Yeah, yeah.
It is a minimum F1, minimum F2. The rectangle is a horizontal and
This
vertical
particular
down.
one. Yes.
Yeah.
So now if you want to say,
Suppose now it is a second case is minimum F2, maximum F1.
so if in this particular case, what essentially happens is you, instead of this bottom, your optimal solutions will be somewhere here, right? You want to minimize F2 and you want to maximize F1.
Yeah, minimum of F2 and maximum of F1.
So maximum of F1 occurs towards right, while minimum of F2 occurs towards bottom. So it should be somewhere towards the right bottom corner, somewhere here.
Okay.
And the other case, like if you just change
Then
it,
it will. then our rectangle will be
Your rectangle will form
horizontal.
something like this.
Okay.
Okay. Now say if you
Yes,
want
sir.
to maximize both of them, then what happens is essentially your ideal point will shift somewhere here, and here your
Mhm.
rectangles will be something like this.
Okay, sir.
And for the last case, you can also have where you want to maximize F2 and you want to minimize F1. Sorry. You want to minimize F1, which essentially means you should minimize F1 should move this direction and maximize F2 should move this direction. So you would be ending up at this particular point.
Mhm.
So your distances should be something like this.
Okay, sir.
And this is for the dominance rank method. So after doing this, you will get essentially a rank for each one of the individuals. And then we also discussed about the dominance depth method, where we essentially kind of do it multiple times. Multiple times in the sense, we'll say for this particular case, if suppose our problem is, we'll just stick to the classic case. Like if you just solve for one of them, say if you want to, we'll do for minimization of both the objective functions. Like if say suppose one of them is maximization, another is minimization, we apply the duality principle. Essentially we kind of say f2 equal to minus of some f and kind of convert into minimization problem and then solve it. So we will stick to this particular case. Both are
Both minimum.
minimizations, and we will
Okay.
take up all the examples so that you can extend it to any other case.
Mm.
Say if your solutions are like this,
Okay.
now we want to rank all of these individuals. Like last week we discussed, we will start with each one of them. For the first one, when you create a rectangle like this, there are essentially no points in this region, which means the rank of this particular point is essentially 1. Now when you want to go to this particular point, there is actually one solution in that
Yes.
rectangle, so the rank of this is 2. Similarly, when you want to do with this particular solution, there is actually 1 in that particular value, so the rank of this is 2. So we'll do that for all of the solutions. And for the next individual, there is essentially 1 point in between, so this is also rank 2. You want to do for this particular
It is
individual.
better to use graph sheet. That will be better.
Yeah, we can use, but ideally what
I
happens is
use
like,
graph sheet.
yeah, I'm for illustration purpose we can use graph sheet, but when you actually implement it on a computer, you won't plot it, right? You need to come up with an algorithm to do this automatically.
Yes, it is.
So we'll actually discuss what algorithm we'll be using and kind of do one hand calculation to see how the algorithm works.
Okay, sir.
We'll come to that later. So last week we discussed about this particular method, and then we also discussed about diversity. There again we kind of told diversity is essentially when you have the same case on the Pareto front, when you have two different solutions, say some ith solution and some jth solution. We essentially, like there could be several ways of measuring it. One possible way could be just we'll construct a rectangle over this particular I and j points and measure the Euclidean distance between them. Basically, I is essentially some f1 I comma f2 I, and the second point is essentially f1j comma f2j. Then we just measure the distance between both the points using the Euclidean distance, like f1i minus f1j whole square plus whole square. This could be one way of measuring it. And we also discussed like how we actually arrive at obtaining diversity within the population is like we externally impose some conditions. We'll just take the we will say like when we are actually doing the crossover or mutation operation, we will do it only when there is enough diversity within the parent individual. So we will measure the distance, we will put some threshold, and we will say if it is less than the threshold, you don't perform the crossover operation because they're going to give the nearby results. Only if it exceeds some threshold, you do the crossover operation. That is what we have discussed over the last week. Now when we come up to the this week's set of lectures, we start with something called, we previously discussed two methods, like preference based and ideal objective solution. The ideal method is essentially you obtaining all the solutions along the Pareto front. In that there are again two classes of algorithms. One is the classical methods. The other ones are essentially our evolutionary computation techniques. So we will get started with the classical methods and understand from there how we can actually implement one of the evolutionary techniques. So we'll take one example. Say suppose you have some function minimize f1 of x, say x comma y equal to minus x, and you have another function f2 of x comma y equal to x square plus y square, and both of them are subject to conditions. We have only one condition which says 0 is less than or equal to xy less than or equal to 1. Now we want to solve this particular problem and obtain the Pareto front for this. So there are several methods in the classical technique. The first one is the weight sum method. The idea in this method is essentially similar to the preference based methods, where we define a new function capital F of x, which is a weight combination of my objective functions.
Classical method?
This is a classical method. We are first starting with classical methods.
Okay. Okay, sir.
So we are defining a new function, something like this, w2 times f2 of x, with some constraints on w1 and w2, which essentially like w1 comma w2 both should be.
It will be fxy.
Yeah, fxy. Sorry, f1 of x comma y. Yeah, thank you. So this w1 and w2 should be within the range 0, 1, and we also have an additional constraint which is essentially w1 plus w2 should be equal to 1. So, or we can write this as f of x comma y comma w1 is essentially w1 times f1 plus 1 minus w1 times f2. So now once we define the new objective function, we solve this particular objective function instead of the original problem. So like previously, when you want to, we want to find the optimal points for this particular f. So the first step is in, okay, we also have the constraints which we need to take into account. So we have constraints which are essentially 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1. So first let us see how the objective space and search space are, and the search space are. Yeah. If you just want to plot the contour plots, of say this is my x and this is my y. If this is my x and y, the contour plots will be something like for the first function f1 is essentially x equal to some constant, so which will be some vertical lines. So these are the contours for my first function f1, and the second function is x square plus y square, which will essentially be some circles, so you'll get some arcs. Okay, it's happened to be the other way. So like the function f1 is defined as minus x, so let's say this is the negative x direction, this is the negative x direction, and this is the positive y direction. Then this is somewhat the contour plot of that particular search space for the variables. Now we also have something called for the objective space. Now if you want to see how the objective space is, we have f1 equal to minus x and f2 equal to x square plus y square. So this is something like f1 square plus y square. So you can see the if you want to plot f2 versus f1, f1 will essentially be negative in the particular range of 0, 1. So say it will be something like this. If this is my value of 0, f1 will range from, f1 is minus x, so it will range from minus 1 to 0. So this will be something the values for my f1. And if you want to see the values for f2 is essentially f1 square plus y square. So it will be a parabolic with a value of 1, and the maximum value of it will be value of 2. So this will be something like this. So this particular space bounded between the two parabolas, like this is actually a parabola. If this is my f1 and this is my f2, this is f2 equal to f1 square, and this particular equation is f2 equal to f1 square plus maximum value of y is 1. So f1 square plus 1. So this highlighted region will be your objective space, and it is our search space. Basically, we are trying to when we are like previously when we discussed, when you want to essentially minimize both f1 and f2, your Pareto front should be somewhere along this particular line, along the bottom edge. So you want to essentially minimize both f1 and f2. So your whatever approach you are trying to use should finally give you a result along this equation, f2 equal to f1 square. So let us see how we will go about doing that. So now we have kind of formulated
Yes,
out.
sir,
Yeah.
sir, this explain me again how this Pareto front this thing, how it will fall.
Yeah, like
At the
our
bottom.
objective is essentially to minimize both the functions, right? Minimize f1
Yeah,
and
yeah.
minimize f2. So it should be towards the bottom left.
Bottom left.
You remember previously we have discussed. So if you want to minimize both of them, it will be somewhere towards the bottom left.
Yes, yes.
So it should be somewhere along this corner. We will find out like what exactly will be that, like what is the equation of the Pareto front. So for that, first method is a weight sum method. Is basically you kind of formulated a new function capital F, that is w1 times small f1 and 1 minus w1 times f2 with some of the constraints. The constraints are essentially the variable bounds. We don't have any other constraints for now. So we solve this problem. The first step is essentially to identify the stationary points. So when you have some capital F of x and you want some capital F as your function, and you want to obtain minimize this function, first step is essentially to kind of make the derivatives equal to 0, del f by del x equal to 0 and del f by del y equal to 0, where if you see the original function capital F is w1 times f1 is basically minus x plus w2 is essentially I want 1 minus w1 times x square plus y square.
Sir, just a minute.
Yeah.
In the figure, at the top you have f2 is equal to f1 square plus 1.
Yes. So that is essentially because this is my original equation f1 square plus y square.
F1 square plus y square, no?
Yeah, the maximum value of y that this possible problem can take is because x comma y lie between 0 comma 1. The maximum value of f2 will be f1 square plus 1. So this will be the maximum outer bound. So only the highlighted region will be my search space.
Okay.
Clear? Clear?
Yes, sir.
Okay. Yeah, so so this is my new objective function. So the first step is essentially del f by del x equal to 0. So this gives me 1 plus twice times x equal to 0. This gives the stationary point like previously discussed, where this particular del f del x equal to 0 will give you the stationary point, that is w1 by 2 times 1 minus W1. Similarly, when we do del f by del y equal to 0, this gives us and my stationary point is essentially 0. So now I obtain two stationary, my stationary point x star comma y star is essentially a function of the weight functions I have chosen. Now as you can see, like
This
yeah,
stationary point, can you explain again?
stationary point is essentially where say you have some function f of x. If in order to
Okay.
minimize or maximize it, we have a condition which says del f del x equal to 0, or
0, yes, yes.
so the point at which this particular happens, like it happens at some x star,
Okay, okay, okay.
that is
That
stationary.
yeah, yeah.
Okay,
That point which satisfies
which
do f to
satisfies
x
del f
equal to
del x
0.
equal to 0 is essentially your stationary point.
Okay, okay.
Now, after obtaining the stationary point, the next step which we discussed in our previous earlier lectures is essentially you need to know whether it is a minima or a maxima. How do we do that?
Mm-hmm. Double once or more we have to do,
Yeah, we call that
and
the
if it is a
Hessian matrix.
positive, if it is a positive, then it is a minima. Negative is maximum,
It's
right?
maxima. So let's just do that. So your Hessian will be del square f by del x square, then x del y. So this is my Hessian matrix. So if I do this for this particular problem, this is my del f del x. So when I apply for a second derivative, it will be 2 times 1 minus w1, 0, 0, and it's 2 times 1 minus w1. So after obtaining the h value, the next step is essentially to determining the eigenvalues of this particular matrix. If you want to determine the eigenvalues of this particular matrix, it will be 2 times 1 minus w1. So what we will be doing is h minus lambda I. Det of this particular matrix is essentially equal to 0. When we do this, we'll obtain equal to 0, which will kind of give my eigenvalues to be lambda is 2 times 1 minus w1. And like previously, from our original definition, we kind of limited the w1 and w2 to be between 0, 1. If w1 is between 0, 1, 1 minus w1 will also lie in the same interval, 0 to 1. So essentially lambda will be a positive number. So like previously we said, like when lambda is positive, it is a positive definite matrix. When Hessian is a positive definite matrix, then it essentially means the solution which I have obtained is a minimal value.
Yes.
So now we have to look at this particular point. So when how I have started is basically I need to know some weights here, W1 and W2. Once I fix some weights, I'll get some solution. The stationary point is this particular solution is dependent upon the weights. Now when I change the weights, I'll get different solutions.
Yes.
So
Weight is we can define.
it is we have to define this value. So what we do, we will generate several weights, several of these weights, and then we get several solutions, and all the solutions will lie on the Pareto front because all of these are essentially minimal solutions. So each one of them should lie on
Yes.
the Pareto front. That if we try to understand it a little more, so let's say I have defined f to be w1 times f1 plus w2 times f2, and I am essentially putting conditions saying del f by del x equal to 0. This kind of boils down to saying del f1 by del x plus w2 times del f2 by del x. Now we can kind of write this del f2 by del x as del f2 by del f1 times by using the chain rule del f1 by del x. If you were to write in that particular way, then this equation boils down to like you can take out the common factor del f1 by del x. So this comes w1 plus w2 times del f2 by del f1. So this entire expression has to be 0. This is equation number 1. And we also have another equation which is del f by del y equal to 0. That will also, if you do the same exercise, you will get something like del f1 by del y times W1 plus W2 into del F2 by del F1 equal to 0. This is my second equation. So when we want to obtain the optimal solution, we essentially want both equations 1 and 2 to get satisfied. So one way could be like you can say del F1 by del X equal to 0 and del F1 by del Y equal to 0. But this particular solution will only give you the minimal value or maximal value, or basically the extremum. Like this will give you the stationary point for the function F1 itself. But if the second factor, essentially W1 plus W2 times del F2 by del F1 is 0, then both equations 1 and 2 are satisfied, which will satisfy my original condition. That means my F will be minimized. So the weights
It's
which
yeah. Sir,
yeah.
Do capital F do X.
Yes.
This gives here also there is a W2 do F2 do F divided by do F2. Do F2 do F1, and another equation and do Fy also it contains do F2 do F1.
Yes.
How it will come?
You understood the first part, like this you are clear?
This do W1 do F1 do X when
plus
we are taking
W2
do
F2 do X.
Okay, first is okay.
Okay,
Another
there
one.
you are kind of expanding do F to do X using this expression. Using the chain rule, you get do F to do F1 into do F1 by do X.
Okay.
In the second one, instead of X, you are just having Y. So this particular one will only get changed to this. Remaining everything should remain the same, right? Okay.
Yes, sir.
So now if we consider this particular equation, W1 plus W2 times del F2 del F1 equal to 0. So like the W1 and W2 had some role in this. So if you happen to see, del F2 del F1 is essentially minus W1 by W2. What does this say? Like del F2 by del F1 is essentially, if you have to see in this particular plot of F1 versus F2, del F2 by del F1 is essentially the slope of the curve at a given point.
Del F2 del F1.
Like if you have X versus Y, then dy by dx will give you the slope of that particular point curve, right?
Yes.
Here we are having F2 and
yes.
F1, so we are getting the slope of that particular point. And where are we calculating this? Is essentially where F is getting minimized. Like this del F2 del F1 is essentially getting calculated where these two conditions are satisfied, which essentially means your F is getting minimized, and that is equivalent to obtaining the Pareto front. So when we are essentially solving this set of equations, what we are doing is identifying the slope of the, getting a tangent. Essentially we are getting a tangent to the points which are lying on the Pareto front. So like just to be clear, in our particular case, we have something like this. So what we are doing when we are essentially finding minimum, say suppose we got some point, like we have got our optimal solution as this, some W1 by 2 comma 1 minus W1 comma 0 or something. So what it will boil down to is identifying some tangent here. And if you kind of
the parabolic curvature.
No, sorry, that's actually a straight line.
This is straight
just
line.
a tangent.
No. This tangent is on that parabolic curvature?
Yeah. It's on the parabolic curvature.
Okay.
So when you kind of change W1 and W2, this slope will change, right? If you choose a different value of W1 and W2, then your dou F2 by dou F1 will change. Then what essentially it means is you get a new point. So instead of here, you might end up getting another point like somewhere over here. Something like this, where the new point will be somewhere over here. So by changing W1 and W2, you are changing the slope of this tangent and you are getting different points on the curvature. This is the main idea of weight sum method.
So how many different points are required to get the diversity?
that is actually one of the limitation with this approach. You can see clearly like there are many different combinations of W1 and W2 that can actually give the same value, same particular slope, right? So uniquely you cannot say that a fixed number of points will give you fixed number of points on the Pareto trend. That is actually a disadvantage with this particular method. We will see how to overcome this in the next method.
It is the ratio of W1 and W2. I can take this ratio to 10 different, so I can get 10 points.
Your W2 is not essentially independent of W1. So this is essentially W1 by 1 minus W1.
Correct.
So once you fix the value of W1,
define,
if you fix your ratio, only one W1 will exist for that particular ratio.
Yes.
Yeah,
for
that
one
is
ratio,
fine.
W1, W2 are fixed.
Yeah, for one ratio, W1 and W2 are fixed. You can't change that.
Yeah, so for one ratio, I will get 1 point.
Yeah, but the problem is, like, if you get only 1 point, which essentially is one tangent, can you be rest assured that you are getting it one Pareto solution always? Like, let me just give you one example. Say you have a curve something like this. Say this entire thing is your Pareto front. This entire thing is your Pareto front, and say suppose that there are actually 2 points which are actually on the same tangent line. Like so for 1W, you can essentially get one of these solutions. You can never know which one of them it is, right?
So I will land up in a local type.
No, the problem is essentially you will not get unique values for each unique value of W1. That is a problem. And there is actually another problem you can see here. Say if you have something like this is what you call the concave. If you happen to just see this particular portion, this small portion over here, that is the concave section of this Pareto front. You will never get any point inside the concave, because if you try to draw a tangent for that concave region, it will actually end up inside the Pareto front.
Yeah.
And if it is lying inside, then all of the solutions are actually dominated solutions. Like as we have discussed previously, inside the search space, what we have are all dominated solutions. You already have something on the Pareto front which is actually dominating the one which is inside. So you are not actually getting what you want. So this particular technique won't work for solution. I mean, for problems which are having concave Pareto fronts.
So in this type of example, here you have shown, I am getting 2 minimum point, that right side.
This one.
Okay. So which one will be the optimum considered?
No, both of them are Pareto solutions, right? So you cannot say which one of them is better. The whole idea is to obtain Pareto solutions. So the problem is I'm choosing only one W and I'm getting 2 solutions, and I do not know, like, if I choose different values of W, whether I'll get different values of Pareto solutions or not. I'm just not sure. That's it. I will get solutions, but I'm not sure whether they are unique or not. But our objective, like previously when we decided what are the goals of my optimization algorithm, it's like I should obtain all the possible points on the Pareto front, and I should rest assured that I have obtained the entire Pareto front. Here I cannot say that. Clear?
Yes.
Yeah. So this particular problem, the second one which we are discussing, is like when you have concave Pareto fronts, this particular technique is not working. Essentially because you are having, like, the way you have defined the problem is kind of leaving you with the slope of the curve. Like you are essentially obtaining tangents, which is why when you are having concave surfaces, you will go on the inside of the objective space. So to eliminate this problem, we come up with the next approach.
It means this technique works only for convex type?
Yes, it works only for the convex type Pareto fronts. So the next approach is the epsilon constraint method. So like previously, the problem is essentially because we define the tangent surface. So now what we do, instead of defining the tangent surface, we just take the vertical line. So The idea is,
This is epsilon.
yeah, it's epsilon.
This is
Epsilon constraint method.
sir. Can you take black ink?
Black ink. Yeah. I don't know if it is any better. Maybe I'll try to darken the pen. Clear?
Yes, sir. Yes, sir. Epsilon constraint. This is also conventional.
This is also classical technique.
Classical.
I hope now it is visible.
Yes, sir. Yes, sir.
So we'll just take the same problem again. So we have kind of obtained that this is my objective space. So in this method, the idea is instead of getting the tangents, we will kind of formulate the problem in a way where I'll vary some parameter which will kind of move this particular line. So this is my epsilon. So what I'll do is essentially move this line. At every position of the line, I'll try to obtain the optimal value. So if the line is at this particular position, my optimal value will be somewhere around here. So somewhere around here will be optimal point. At the next instance of time, I'll move this line somewhere here. When the line is moved, my new optimal point will be somewhere over here. So again, if I kind of move it, then I'll get a new point. I'll move it till if you move somewhere over here, then essentially you won't get any solution in the feasible region. So that is when you are kind of out of your feasible region. So when you start moving from one edge where you have all feasible solutions to again you continuously move it across the entire domain of your F1. When you completed the search, you kind of obtain all the solutions along the front. This is the idea here. So like we'll put it mathematically. Say suppose I'm considering the problem as like our original problem is minimize F1 and minimize F2. This is essentially minus x. This is x square plus y square. Now I'm kind of changing this problem into a new way where I'm saying instead of minimizing two functions, I'll minimize only one function. Previously we defined it as a weighted combination of F1 and F2. Now I'm saying I'll just minimize F2. I'll not use any weight combination. I'll minimize only one function subject to, I'll add a constraint to it saying my F1 is essentially less than or equal to some epsilon. Or maybe F1 is greater than or equal to epsilon. You can kind of pose your constraint in your own way.
So this selection, whether it can be taken F1 or
Yeah,
F2,
it can be chosen.
less than or equal to epsilon.
Yeah, it can be chosen anyway. I've chosen this particular way
okay.
because I'll tell you, like it just makes the simplification easier. So you can see like F1 is just minus x, F2 is some complicated function. So if I define x square plus y square is less than or equal, solving will be difficult. So I've chosen this way. But you can take anything.
Okay.
So I'll change my problem to this particular formulation and we'll solve this from, we will solve this. So we'll just see here, if you kind of formulate it in this particular way, you are saying essentially minimize x square plus y square subject to the constraint minus x is less than or equal to epsilon, or the other way around, you can say x is greater than or equal to minus epsilon, whichever way you formulate it. But this is a type of problem we have seen previously. Like if you want an optimization problem with an inequality constraint, the way to go about it is using KKT conditions. So let's just write them out. For this particular case, you define some function L. You want to minimize the function x square plus y square. Previously, we have seen that for this, you need to convert your inequality constraint to be less than or equal to 0 form. So if you can change this, this will be minus x minus epsilon less than or equal to 0. So it's u1 times minus x minus epsilon. And then you have certain other conditions, which is essentially u1 times minus x minus epsilon should be equal to 0, and you also have another constraint which is u1 should be greater than equal to 0. This set of all three conditions will give us are essentially this. Okay, one second. This along with your other conditions. I hope you are aware that we are actually uploading the session of this on YouTube, so you can actually revisit later if you want.
Okay.
You like this session will
Is
be
this,
recorded and uploaded in YouTube.
KKT condition, can you? Okay, sir.
Okay.
What will be the name, number?
Number for
This to locate this in YouTube.
like if you happen to see the NPTEL lectures, like where the professor is uploading, in the last one there will be the live session. If you can click on that link, there all the YouTube recordings will be there. You can access from
yes,
there.
sir. Oh, yeah.
Okay.
Okay, sir. Sir, can you explain a bit more about KKT, applying KKT conditions? This I could not understand.
Okay, we'll just take a general problem then instead of the specific, and then we'll come to the specific problem. So,
yeah, just a briefly. KKT
so
conditions.
You have some function f of x. We'll just stick to one dimension. You have some function f of x subject to some constraint g of x is less than or equal to 0. You want to minimize this function. This is the classic case where you kind of want to use KKT condition. So idea is to minimize f of x subjected to some constraint. So what we are trying to do is we will define a new objective function, say L, which is essentially f of x plus some constant u times g of x. And what we do is essentially minimize this L of x. Minimize this function.
Sir, u is a constant?
We'll come to that. U is essentially a constant. So when you want to minimize L, so the same condition for stationary point, you apply del L by del x equal to 0. So this is actually one equation, and you essentially have u is a constant which is an unknown. Like you won't determine it; it has to come from the set of equations. So how do we get that? We need another equation for that. So minimizing L should be equivalent to minimizing f of x. So this particular term should not have any contribution to L. So that is my second equation. That is u times g of x should be equal to 0. And we also have another constraint where on this particular u, like u cannot be any number. If you want to minimize L, and this particular constraint has, it is not like g of x should always be 0. The idea is g of x should be some negative value. If g of x is positive, my L should be increased. So you define u to be greater than or equal to 0. In this particular scenario,
if gx is greater than 0, then what will happen?
If gx is greater than 0, and if suppose your u is less than 0, in this particular case, u times z will be negative. So the value of L will essentially decrease, which should not be the case. Like L should be minimized only when you are in the feasible region.
Okay.
So to prevent this from happening, you provide an additional constraint, which is u should always be positive.
Okay.
So now here you have two equations, and you essentially have two unknowns. Like your unknowns are basically the stationary point x star and this particular constant u. So two equations, you solve them and you get the constants. That is the idea for KKT. We'll just see now one example how we solve this here. So if we apply the same conditions here, so here your objective function is x square plus y square, you are trying to minimize, subject to this particular constraint g of x less than or equal to, like this has to be formulated in the way g of x less than or equal to 0, which is this minus x minus epsilon is less than or equal to 0. Then you define a new function L of x. Here we have two functions, so L of x comma y is essentially x square plus y square plus u times the constraint. And the next condition is u times z equal to 0 is this particular constraint. And then you also have additional condition stating u1 should always be positive. Now we have another, the essential equation is del L by del x equal to 0 for obtaining the stationary points, and del L by del y equal to 0. This first equation gives us 2x minus u1 equal to 0. This particular equation will give us 2y equal to 0. This is essentially y star equal to 0. So this is one stationary point. Here you are having x star equal to u1 by 2.
Yeah, the stationary point we will get.
Yeah. Now we have another equation which is essentially u1 times x plus epsilon equal to 0. So we have two possibilities, either u1 equal to 0 or x equal to minus epsilon, or you can have both of them. Any of these conditions can be true. I think we have, okay, there is some small confusion here. So if you happen to see this particular line here, what we are trying to do is essentially find this particular overlapping region. So for our particular problem, we are saying f1 should actually be less than epsilon. We have defined it in that particular, okay, fine, it's clear. So
this line is at epsilon, no?
This line is at epsilon.
X is equal to minus epsilon.
This is x equal to epsilon. I mean,
yeah,
that is the kind of the
x is
left
equal to
side
minus
boundary.
epsilon.
That is the boundary for it.
Yeah.
So now when we solve this, like you have here x star equal to u1 by 2. So if u1 equal to 0, you get a point x star equal to 0. That could be 1 point. And there could be other case where u1 is not equal to 0. If u1 is not equal to 0, then your x should be minus epsilon. So there are essentially two possible solutions. So if we see here, the first case x star equal to 0 will correspond to this point, that is 1 point for the Pareto optimal. And the second case where x star is essentially minus epsilon, or you put it in way x star, this x star is essentially minus f1, that equal to minus epsilon. So this comes out to be f1 equal to epsilon. So that is our next point, this particular point. So when you solve this problem, you are essentially getting two solutions, one at this boundary, one at this boundary. So when you continuously vary the value of epsilon, like if you vary the epsilon, move this line around here, then you can keep on getting points.
Not visible, sir.
Sorry?
Not, I could not see whatever you have explained.
Okay, one second.
On the screen. There was no change. Screen did not change.
One second. Let me share my screen again. Yeah, so I was saying, if you were to move this particular line, like previously it was here, now when you are gradually moving this value of epsilon, at a new point you will get a new solution somewhere here, and like eventually you will get this entire line.
Okay.
Here. So like here, like in the previous case when we are considering tangent, we have a problem with concave surfaces. But here, since we are not having any tangent, it's essentially one straight line that is moving. We don't encounter any problems with concave or convex. Like it works for both the cases.
Yeah.
So this is epsilon constraint method. And then there is some
so this can be used in all problem if you don't know whether it is concave or convex.
Yes. This can be used for it is a kind of a general one. But you can see the problem here is essentially in this second case. Like here, you have only two objective functions, so you have one constraint. So you are satisfied with it. Say you are having an m objective function, like you have m objective functions, say capital M, let's say m objective functions. Then when you are formulating the epsilon constraint problem, what you will be doing is trying to convert into a single objective function. So there will be one objective function and m minus 1 constraints that you are additionally adding to your problem. And solving it using KKT will get additional, like the complexity will gradually increase as your number of objectives are increasing, and because essentially your constraints are increasing and your equations are increasing. When you have a multi-dimensional problem with so many objective functions, then this cannot be easily scalable. Then we might have to resort to one of the earlier methods we have discussed, like You define some penalty function, like we have discussed various penalty functions that you should be using in evolutionary computation techniques. Maybe the Dave's approach or some approach where you kind of take a weighted combination of all these constraints and add them to your penalty function and then minimize the penalty function. We have to resort to such kind of approaches. So this is actually the limitation with the only limitation with this approach is essentially because of this additional complexities you are getting by adding more constraints.
Yes.
So the next idea is, okay, here we have considered only single line. The next method is a kind of a general way where you kind of have, instead of considering only a single line, you will consider a rectangle. Or we'll just stick to the general method first. So that is the Chebyshev method. Here what we will do is also, like all these classical techniques are based on one single idea. Like the idea behind all these classical techniques is when you have a multi-object optimization problem, you will try to have convert it to single object optimization problem by using some parameters, and you vary those parameters. By varying these parameters, you will solve a set of different single object optimization, and solutions of each of these single object optimizations when combined will give you the Pareto fund. That is the main idea behind all these approaches. Even this particular method is also relying on the same. So here the idea is when you have something like minimize F1 and minimize F2, we will convert this into some new function. So we will use small l of x comma y. We will maximize the distance from, we'll take some weight combination of f1 minus z1 star. I'll define what z1 star is. W2 times f2 minus z2 star. We'll define now what z1 star, z2 star are. If you can recollect from our previous discussions on the getting dominance rank or all those methods, the idea is like you have something called like, we just see that particular approach. We resorted to this particular point towards one of the corner and said like, okay, we essentially want to move towards the corner. And if you see all the points which are closer to it will eventually be the Pareto front, like we'll be lying on one of the Pareto front. If this particular one is not existing, say if it's not existing, all these points which are closer to this particular point are actually forming the first rank, like they will be the Pareto optimal solutions. So the points which are closer to this will be lying on the Pareto front. That is the idea for this approach. So what we will do is we define one point which is our ideal point. So how do we get the ideal point? Ideal point is essentially when you solve each of the optimization objective, like you have several, here we have say F1 and F2 as two optimization problems. So we solve only F1, like we do not worry about F2 and obtain the minimum value of F1, that is corresponding to Z1 star. Similarly, we solve F2 without worrying about F1, then we get a solution as Z2 star. This particular point, say we consider here the minimum of F2 without considering F1, this particular one minimum point will lie somewhere around here. And if you want to minimize F1 without worrying about F2, the minimum value will be -1. So it will be somewhere over here. So the point of intersection of these two lines. So minimum of F1 and F2 will be somewhere over here. So this is what we are calling an ideal objective vector.
Here, when we minimize F1,
yes,
then Z1 star will be 0.
No. F1 is minus x, right? And x is like F1 is essentially minus x.
Okay.
0
okay,
less
yes.
than or equal to x less than or equal to 1. So Z1 star will be -1.
-1, yes.
Okay.
Yes, yes.
So this is what you call an ideal objective vector. Like you can see in this particular case, like this particular point is actually not lying in our feasible space. Our feasible space is essentially this, whatever is interior in this particular region.
Yes.
So ideal objective vectors usually do not lie inside the feasible space. It will lie only when you have something called non-conflicting objectives. Say you have F1 and F2 which are not conflicting with each other, then how your objective space looks is something like you have one, it will look something like this. When you have your objective space of this particular shape and you want to minimize both of them, you will essentially have one particular point that will be your ideal objective vector, or you can kind of consider it the other way around. Just consider a rectangle. Like if your objective space is just a rectangle, so that F1 and F2 are not related to each other. That is what this particular line is. Like if F1 and F2 are no way related to each other, then it will be a rectangle, just a rectangle in the objective space. So this will be your entire feasible region. So when you want to minimize both F1 and F2, if you want to minimize both of them, then you only have your ideal objective vector will be this particular point, and that will be only your solution. You do not have a Pareto front here. Like the Pareto set essentially has only one point in it, and that is this particular point. So only when F1 and F2 are not related or not contradicting with each other, you kind of have this jet star being inside the feasible space or being the solution. But usually it won't be inside the feasible space. So the next idea is, okay.
So they are not contradictory. If they are not contradicting, means one is both are minimum or both are maximum.
Not contradicting means essentially you can kind of change one without affecting the other. So if you want to minimize F1, your F2 can be either, like you can independently minimize both of them. There is no dependence among both of them. So say suppose that is not what actually happens in your practical problem. Say you want to buy a phone which is of say highest quality, or you want to manufacture some product which is of highest quality, and at the same time it should be the cheapest.
Yeah.
Those are kind of contradictory. But now consider another example. Say you're driving and you want to move from some place A to place B. You want to minimize your total distance. At the same time, you want to minimize your total time.
Yes.
If your total distance is minimized, more or less total time is, they are more or less kind of, you can kind of minimize them independently.
Same time.
It's like if you minimize one, the other will be anyway minimized. So you don't have the concept of non-dominance, and hence there is no concept of Pareto.
Yeah. I think here if F1 and F2 both are minimizing type, then most likely they will be non-contradicting type.
Like in practical scenarios, you will have contradicting. Like only if they are contradicting, you're actually trying to optimize something. Like you are optimizing essentially because you have some trade-offs and you do not know which one to compromise. So you are resorting to all these methods. So in this particular case also you can see like F1 is minus X. So if you want to minimize F1, you essentially have to increase the value of X. But if you increase the value of X, your F2 will increase. But you want to minimize F2.
Yes.
So these are also kind of contradicting. They have a common dependent factor which if you try to change, one will increase, other will decrease, but you essentially want both of them to decrease, which is not going to happen. So you need to find a trade-off between these.
Yeah.
Okay. So
for trade-off, we are using that weight method.
No, we are discussing only the mathematical techniques. Finally, we are not deciding what we see. When we obtain the Pareto front, all the solutions on the front are basically, you cannot say which one of them is better than the other. You are only saying that these are the set of solutions which you are not able to say which one is better than the other. Out of them, finally you need to choose only one for your decision. Say if you are having some client, you have to choose only one particular configuration of your missions which will give you some level of quality and some cost for it. That has to be given at that is what we call the high level information. Someone has to tell you, say if you compromise on the quality by say 10%, what is a cost decrement you are going to get? Is that acceptable or not? That has to be something which is beyond the scope of this particular set of courses we are having in this particular course.
So from the Pareto front, we cannot pinpoint the final solution.
No, Pareto front will give you only possible solutions. No,
Yeah,
it's
it is a
not a
set of
problem with the
solutions.
method. It's basically about your input. You don't have any
Yeah.
information. You are essentially saying there are so many possible solutions. Out of them,
Hmm.
these are the set of solutions which you
Hmm.
are not able to compare with each other. There are other solutions. So if you consider any points inside this region, any point inside this region is actually inferior to points on this. Any point on the Pareto front is actually better than the point inside. That is for sure. But
But for
within the
practical
points on the Pareto
solutions,
front, sorry, for?
for practical application, we need a final solution, single solution.
Yeah, but the final solution cannot be told by the person who is actually doing the optimization. That should come from the management. Say, suppose if you are in some manufacturing
Hmm.
plant and you're kind of producing some products or something, the quality
Yes.
and the cost, say, suppose you're working on quality versus cost. You know, you want to
Hmm.
minimize cost, you want to maximize your quality, and you kind of obtain some particular configuration or some particular way to manufacture, or say some particular arrangement of your devices, or maybe your process in such a way that will minimize this, but only one configuration will not give you this. There might exist several possible combinations which will give to several costs and several quality aspects. But who can tell you like how much cost is acceptable in the market? How much, like it will depend on several other factors. Depending on the market, maybe for some products a higher cost with a higher quality is what is acceptable. And in some products maybe
Hmm.
quality you can
Hmm.
compromise on quality. That you cannot say from this, right? That is not actually put into this problem.
Okay.
If you actually have that information, then you essentially don't have two objectives. Then you are kind of collapsing into a single objective function. So if you know that okay, there is a market which kind of has quality, say some 80% is fine and cost is what that is more important. Like even if you compromise on quality, they don't mind, but the cost has to be cheap.
Hmm.
Then you will formulate only
Then we
single
have to go
objective
for
function.
yeah,
You have to
preference
minimize the
type.
cost. That's it, right?
Means preference type method we have to use,
Yes,
converting it in a single objective function.
yes. If you have the, if you know all that information beforehand. These techniques are
Yes.
basically for those where you do not have that high level information.
Okay, sir.
So here, once we define this ideal objective vector, the next step we will be doing is to solve the optimization problem in such a way that basically the distance between these 2 points is minimized. So one point is inside. So the distance between the ideal objective vector and this point is what we are trying to minimize. As the distance is gradually getting minimized, and we also have the constraint that it will be anyway in the feasible space. So eventually all these points will come and stop at this particular Pareto front.
Yes.
So this is what we call the Chebyshev method. There is just another variant of this. That is a Benson's method. It is similar to this particular approach, but only different in one particular way. So what we do, instead of measuring distance from the ideal objective vector, we actually define a point which is inside. Say we this particular point, I fix this particular point, and what I try to do is maximize the distance of every point from this particular point. When I try to maximize the distance, what will eventually happen is all these points will tend to go towards the boundary.
Yes.
And since your objective function is formulated in such a way that you want to minimize both F1 and F2, they will eventually reach this particular boundary instead of the other boundary.
Mhm.
This is another approach called the Benson's method, but the problem here is essentially how do you know which point to choose within the feasible region.
Yes. Yes.
The problem is very sensitive to that, so usually do not encourage to use this.
In
But
earlier
these are
methods,
all
we have to
this.
measure from the Z1 and Z2, right?
Yeah, you need to measure from Z star. Okay, or basically the
Z star.
ideal objective vector.
Yeah, yeah. So whichever is having least distance, that will be better.
No, not like that. We cannot say whichever is the least is the better. We are only saying when you try to minimize the solutions, what if you are starting with some solutions inside the feasible region, eventually the
Mhm.
solutions will improve to moving towards the boundary. And once reaching the boundary, they cannot come out of it. And this boundary is essentially your Pareto front. That is what we are saying.
This week, in one way we can do, we are every time we can measure the distance from Z star point, and when that distance comes to the boundary at the boundary side, then that will be the solution.
Yeah, but
Because
you do not know boundary beforehand, right? Like here I am showing you the
yeah,
picture,
before
but
boundary.
ideally you do not know what is a boundary, and the problem is essentially to identify the boundary, and all these methods are essentially trying to do the
Yeah,
same.
yeah. Okay.
Like if you start even from the first method we discussed, like weight sum method, there also is the same. You kind of obtain
Mm.
some solutions, you obtain some problems, like, but we do not know what exactly is it. Like we do not know the boundary. Even in the epsilon constraint, like anywhere we do not know the boundary. The objective is finally get all these solutions, and when you combine all these solutions, the locus of all of this is a Pareto friend. Like you change the weight
Okay.
parameters in the here also you have the weight parameter. By essentially varying this weight parameter, you get several solutions. Once you combine all these solutions, that is
Yes.
when you get this Pareto friend.
Yes.
So like if you just happen to see all these methods, it's the same idea. You start with some point, some parameter, you vary the parameters, get several points, you combine all of them, and you get the Pareto friend. And that is exactly what we are going to use in our evolutionary techniques. Like if you happen to see genetic algorithm or any other method, you initially start with a set of solutions, and then you gradually try to improve those solutions.
See, in this classical method, how many set of W and W2 are required to get Pareto friend?
That we cannot say beforehand
Because we
itself.
have to change the W and W2.
Yeah, you can start with some set. Like we cannot say beforehand. It depends on so many factors. Like if you resort to this epsilon constraint method, here is like each value of epsilon will give you only one point on the Pareto front. So say
Yes.
suppose you want 10 points on Pareto front, then you need to try with 10 different values of epsilon. There
Yes.
is no other way. And you do not know
Mm.
beforehand how far is your Pareto friend. Like basically you do not know in what range. For in this particular case, say you know the value of epsilon, like it will range from 0 to whatever is the minimum value of one of the objective functions, because if you go beyond that, then it will be in the infeasible. So if you have some epsilon in this region, that is infeasible, there is no point. So here you can kind of say, but if you want stuck with this weight sum method, there you cannot say beforehand how many W1s you want.
Yeah.
So you have to just start with some number and see how it works out.
Okay.
But we can do all of this parallelly in our original framework of evolutionary computation techniques, like even the genetic framework, genetic algorithm framework or something. The idea for that is the
Which
next
say
NSGA.
again? I could not hear. Uh,
Yeah, I was
NSGA.
saying, yeah, it is GA. So basically, here we are kind of varying the values of W1 and obtaining different points on the Pareto front, right? So
Mm.
what I'm saying is, you finally want the set of solutions on the Pareto front. So what we will do, say suppose you want some 10 points on the Pareto front, what we do, we'll start our genetic algorithm with 10 random solutions, and we keep on improving them till they reach the Pareto front. And our objective is essentially to reach the Pareto front and to have sufficient diversity. So if
So, is there method to know that we have reached the Pareto front?
that is what we will try to formalize here. Say, how do you know if you have reached the
Okay.
Pareto front? Basically, the idea for the Pareto front is that all the solutions on the Pareto front should be non-dominated.
Non-dominative. Yes.
So if we can kind of come up with some metric which tells us all the whether the solutions are non-dominated or not, then that will be our fitness function.
Mm.
So if that fitness function is not changing over iterations, which means we have converged to our Pareto front. Like
Convert. Yes.
so, if you have some space like this, say minimize f1 and f2. When you initially start with some solutions, you might get some front like this, which may not be the Pareto front. But as you keep on changing, that will get of improve till you reach this particular place where actually your
Mm.
solution solution has converged, in the sense it is not changing over iterations. So that is your Pareto front. So if we can use our genetic algorithm to kind of solve this problem,
Okay.
and that essentially is the NSGA algorithm. NSGA is essentially non-dominated.
Now this is EC method. Huh?
Sorry, yeah, it's an EC method. So if you were to remember the previous case, the general steps in genetic algorithm, the first step is essentially you start with some population, or maybe we should start even further. We'll just stick the general algorithm. The first one is the solution representation. We discussed two cases previously. One is the real encoded and other one is the binary encoded GA. So you choose one of them. The next step, you decide what is your population size. Say if your N is your population size, and how many generations you want to run. Say let's say capital T is your number of generations you want to run. Once you finalize on this, the next step is essentially to initialize your population. We have seen how to initialize our population. Once you are done with initializing population, like here, like none of this is going to change. All the steps will remain the same as we have discussed previously. After initializing the population, the next step is essentially evaluating their fitness. This we have seen is if you have an unconstrained problem, then your fitness will be essentially equal to your objective function value. When you are having constraints, then you need to reformulate your problem using some of the penalty functions we discussed, any of the penalty function, and then take that penalty function value to the fitness. So this step is also not going to change, like it's going to be remaining the same for the previous case and even in this particular case. After you assign the fitness values, after you calculate the fitness for each of the solutions, you actually start into the next loop. Essentially, you have a counter for your generations, and that should be less than this maximum number of generations you have decided. And in each of these loops, the next step is essentially you need to do the tournament selection. We discussed about the tournament selection. So you select some of the solutions. We call them the selection. So previously, how did we select it? In case of binary tournament, we randomly pick two solutions, compare their fitness value, and told which one of them is better. You select that. Like that one wins the tournament, and you select that particular individual. But that approach is not going to work in this particular case, because here we might actually end up like the comparison between two individuals is not straightforward like the previous case. So this particular step is where some changes have to be introduced. So we need to look into these steps again. And once we do the selection, the next operation is essentially your variation. That is where we do the crossover and mutation. And while doing crossover and mutation, you do not essentially worry about the fitness values. So you just do it using whatever the individuals you have chosen. This crossover and mutation will only depend on the way you are representing your solution. So this particular step is also again not going to be affected by this, but when you kind of change from single to multi-objective. Once you are done with variation, like that is essentially crossover and mutation, the next step is again you need to identify the survivors, that is say offspring. So or okay, even before that you need to again evaluate the fitness of whatever the new offsprings you got. So let's say you evaluate the fitness again. Evaluating fitness is just getting the objective function values for each of the individuals. That is not going to change. But when you come to survivor, this is where out of all the, when you have the pool of both parents and offsprings, you need to select the individuals which should go for the next generation. And it is in this step that again some changes have to be made. And once you are done with survival, you just increment your generation number, and you kind of end your loop. So basically now we essentially have only two steps, like the selection operator and the survivor operator, that are going to be changed. And however we are changing, the idea is these operators should somehow reflect the information that we are going to have about the solutions which are lying on the Pareto front. So how are we going to do that? So we have the selection operator is essentially your filter to kind of having better solutions. So it should solve two particular problems. So first one is you have non-dominated solutions. Second one is that they should be diverse enough. And even the survivor also should take care that it solves these two conditions. So how do we go about measuring the dominance of the solutions? We have discussed about three methods, like the dominance rank, the dominance count method, and the dominance depth method. The idea there is like when you have two solutions, you are able to compare them, you are able to rank them, so that you can say whether one solution is better than other. So if you are having a rank one solution versus a rank, like if you want to do some tournament selection operator, same like the previous case, in the tournament when you have two individuals, say one is rank one, say you have two individuals P1 and P2, this is of rank 1 and this is of rank 2, then you definitely know like rank 1 is better than rank 2. So this is the idea for this. So we need to kind of come up with the dominance rank for each of the individuals inside the population. So how do we actually assign this? Like the previous method which we discussed is like you just take a box and then you fix one corner and kind of draw a rectangle over there and see how many points are lying within the rectangle, plus 1 will give you the rank. But that is not how you, like you cannot implement it directly in a computer. So how are we going to do it? We'll stick to the algorithm.
Sir, here we should use a dominance rank method or dominance count method for selection purpose.
No, we will be using actually dominance depth. Essentially, we will use the
Dominance
dominance rank. Yeah, dominance depth is essentially dominance rank applied several times. First, you apply the dominance rank, obtain all the individuals with rank 1, and then you remove them from the population. Out of the remaining population, again you
But
find
rank and count,
rank. It's rank.
rank and count, they are complementary, like.
No. Like we have seen in the previous week, like when you apply the dominance count method, all the individuals on the first front will essentially not have the same value of count. Say what I mean is like, say if you have something like this.
Rank means by how many individuals it is dominated by.
Rank. Yeah, you are essentially saying count and rank are complementary, right? Which cannot be always.
Yes.
Say if you consider this particular
Okay.
case here, the count of this is 1, sorry 0, and when you see the next one, this is 1. If you happen to see this is 2.
Yeah.
Say you have another point here. So this also has a count of 2. This has a count of 0, or maybe we'll just say something like this. The count of this will be 1, this is 0, and this is essentially 3. So if you happen to see like this particular point, these 2 points, both of them are actually rank 1, but their count can actually be different.
Yeah.
So we essentially want the ones which are having the same rank, in the sense all of them are having rank 1. So if you resort to count method, they can
Rank
actually
1.
have different values. So we will stick to the rank, like we will use the rank metric.
Okay.
But how do you actually get the rank method is basically, say you have n solutions, like n individuals, and say you have m objectives.
Yeah.
How do you find the rank of them? It's like you just say, like you just loop over for I equal to say 1 to all the objectives or all the individuals, over all the individuals, and for each individual you'll again start with another loop for j equal to say 1 to n. Then you again have another loop which will kind of iterate over your number of objective functions, and it will kind of, now what you do is essentially you compare each one of them. Say if f is your function, fk will give you for the kth objective function, fk of I is actually less than fk of j. In that particular case, then you kind of repeat for all, like this will be repeated for all the individuals. And if this is true for all the cases, then you kind of say ith individual has a rank of 1. Or maybe if it is rank 2, you can get that
This
as well.
These are three loops.
Yes.
M is okay for objective. N is individual. Why another loop is there for I is equal
So
to 1 to N?
yeah, so when you go through each and individual solution, say if you want to calculate the rank, if you are having one individual here and so same way other individuals, so you start with one individual and then you compare these individuals with all other individuals. So this the bigger circle is for the
Okay.
second loop. So after you do with this, then you go to the next one and then you start with all this one again. So you see the first loop is essentially the small circles. Then you essentially go with all of them. Again you select one small, the I value changes to this, then this will be your J loop. So for
Okay.
each and every individual solution, you want to compare it with all the remaining solutions.
Yeah.
So you essentially need two loops for that, and again you also have another that is essentially your number of objective. Like if you have m objectives, then you need another loop for all these m objective functions. But after doing all of this, what you will get to know is essentially only one single value. Like you will know whether that particular ith individual is of rank 1 or not. If this is satisfied for all the values, then I has a rank of 1. Then you go to the next solution. Again you do the same. You know whether it is of rank 1 or not. And you kind of repeat it like this particular thing. You have to repeat n times again to know, to get all the values within that particular having some rank 1. Like let me be clear. So with this you will get only the solutions which are of rank 1. But like we discussed, we need to identify
Yeah.
solutions with rank 2, rank 3, rank 4. So what you do, once you get rank 1 solutions, you remove them from the population. Again you apply the same technique to get rank 2 solutions. Again you remove them, again you do it. So that will be
Okay.
like in the worst case scenario, that will be like here it is m n square will be the order of this particular algorithm for finding one rank of one. For finding for the first case, for the first front. Now if you want to find the second front, you have to do it again. So this will be again n. So this is like if you have idea follow this particular approach, this will be order of mn cube.
MNQ.
Yeah,
Yeah.
if you use this particular technique, but the actual implementation of NSA algorithm has another algorithm which kind of solves this problem with mn square. How did they do it is like if you see here, we are essentially doing when you kind of say for this particular individual, I kind of compared with all the individuals and I know this is my first individual. And again, when I want to compare it with the second time, again I'm comparing with all the solutions. So like there are some operations which are kind of overlapping with the first one, which I essentially don't have to do. If I can somehow store the information about what happened previously when I compared these individuals, I can kind of use it in the next time when I iterate it. So that is, we will see that algorithm.
It will require huge storage.
No, you don't have to. It won't be huge storage, but essentially your storage will increase a little. Like
Huh.
there is this trade-off always. If you want to decrease your complexity with respect to your time, then you need to have something that has to be stored to increase your to essentially reduce your time. There is this trade-off always. So this is that. Is this visible first?
Can
Visible,
you
right?
change the background white? It is gray now.
Yeah, but I cannot change the background now. Okay, maybe I'll just explain you how the method actually works.
Ah,
We will take one example maybe. That would be better. One second.
okay, sir.
This is visible, right?
Okay.
Say we have two objective functions, say f1 and f2. For now, I'm just kind of defining some random values. Yeah, say suppose we have 6 individuals and these are the values of f1 and f2. What we are trying to do is we need to identify the solutions. Say it will be the same problem as minimize f1 and minimize f2. So let us just plot these solutions first. So from our previous case, we can kind of get the ranks directly, like we'll just put the indices first. So let me say the index or this, and we'll label each of these points. So 0.632, 0.038 and 0.741 is essentially 0.3. This is my index 3. 0.481 is index 4. 0.892 is index 6. 0.694 index 2. And 0.632 is index 1. 2 is index 1. 0.132 is index 5. Okay, these are my 5 individuals. So the first step is essentially we will define a matrix called SP. SP is essentially, so we'll just see the loop. So in this particular loop, we will go only once, and when we compare them, we'll here store the information about the comparison. So we are essentially define two variables, SP and NP. So SP will have information about how many solutions are going to be there that are on the other side. In the sense, if you are comparing one solution, you essentially can divide it into two regions. All the solutions in this particular region will be essentially the ones which are dominating the given point, and these are the ones which are actually dominated by the given point. So we will be keeping track of these particular solutions and this particular quadrant, only these two quadrants. SP will track one of them. SP will track this particular values. Okay. And NP is going to track this particular values. So NP will tell you how many points are actually dominating the given point, and SP will tell you how many points are actually dominated by the given point. So now, when you if you define it in this particular way, and you happen to find if NP equal to 0, if NP equal to 0, essentially means there are no points that are dominating the given point, which means this particular point will belong to rank 1. Now, once you obtain all the solutions in rank 1, then you go to the next step. We will see how this is done. So this is the stage 1 of the approach. So we will kind of split this original thing into two stages. In the first stage, we kind of obtain all the solutions on the front rank. In the second stage, what we do, we will use the information about SP. SP is actually the ones which are actually dominating the given point. So once we know all the points on the first rank, we will go to each and every point and see how many points it actually dominates. And again, inside that for those particular set of solutions, we will actually do apply the same steps again. And again, identify which are actually of the first front in the same. And keep on iterating till we obtain all the fronts, like first front, second front, third front, till there are no fronts, till there are no solutions on that given front. So here, if you want to kind of put it up, so there are essentially two things. One is your SP, and the second one is your NP. So we'll go solution by solution. For the first solution, over here, there are actually more points here, I guess.
At the bottom we have more points.
Yeah. I'll just draw this again. Point 611. Yeah, it is essentially the first point, so it doesn't matter. 0.611 is your first point. 0.762 is your second point. 0.053 is your third point. 0.666 is your fourth point. 0.416 is your fifth point, and this is your sixth point. Okay, so for each and every point, say for the first point 1, what we do, we will compare with each and every other solution and see how many points are actually dominated by the given point and how many points it is getting dominated by. So for 1, we can see like there is no point that is dominating 1. So SP is essentially, like if you see in the previous case, SP is the ones towards the other side of it, which are actually getting dominated by 1, and NP is essentially the ones which are which actually the given point is getting dominated by. So here SP for this for the point 1 is there is no
NP is basically rank.
These 2 points, 2 and 4, sorry.
NP
NP is just a counter. It just counts the number of points which are actually dominating the given point.
Okay.
So for point 1, there is actually no other point that actually dominates it. So
Yes.
NP will be 0. And SP is actually to the other side. You essentially have 2 points which are actually getting dominated by 1. So those 2 points come in SP. So your SP will be 2, 4, and your NP is essentially 0. Okay, the points changed. Okay, understood. What's the problem? I might have to do this again. Okay, we will stick to the writing itself. So say suppose we have some serial number, we'll put some index in an F1 and F2, and we have only 4 individuals with the following values: 0.1, 0.3, 0.2, 0.4, 0.1, 0.5, 0.5, and 0.3. Say we have only these 4 individuals, and we want to compare each one of them with the other. The first one is essentially identifying SP and NP for each of the individuals. Now, to calculate these things, we will compare the first one with each and every solution. So when you compare solution 1 with solution 2, so we will just put the markers here. So it will be F1, F1 of next solution, F2 and F2. So first case we are considering comparing 1 and 2. In 1 and 2, F1 for 1 is actually less than F1 for 2, and if you want to compare the F2 value is also less than F2, which means 1 is clearly dominating 2.
F1 is less than.
Yeah, you can just
Okay.
look at this.
Yeah,
F1,
yeah,
1 is
yeah.
actually less than 2, and similarly for this
Yes, yes.
case. So,
One is dominating.
1 is actually dominating 2. So, I'm kind of writing in this particular way. 1 is dominating 2. Now, in the next step, you compare 1 with 3.
P.
So, this is kind of equal, and F2 is actually less than. So, if we are kind of say 1 is less than or equal to 3. Similarly, we will compare 1 with 4. 1 is actually greater than this, and F2 is equal to this. So, here we can say
Yeah.
like 4 is less than or equal to 1.
Yeah.
Or maybe we can write it other way. 1 is greater than or equal to 4. So, by seeing this, like we have seen, NP is basically you add to NP, you increase the counter of NP only if a given solution, if P is actually greater than Q, you add it to NP. SP is basically the one where P is actually less than Q. Like if P and Q are two solutions, you increment the value of NP if P is greater than Q. Like you can see here, you increment the value of this particular value of NP only if there are some solutions in this particular domain. There will be some solutions in this region. There will be some solutions in this region only if P is actually greater than that particular solution. So that is this particular case. And if P is less than Q, then you kind of add it to the SP.
What is P and Q, sir?
Yeah, here in this part, P and Q are essentially your solutions here. So if this is my P, this is my Q.
Okay.
Like the P is the first iteration, the one I am like in this loop, this I will be the P value and this will be my Q value.
Okay.
So, okay, for the first case, 1 is less than 2. So it is going to the second case. So it should go to SP. So 2 will come to SP. The second case, 1 is less than or equal to will also be SP. So 3 also will go to SP. The third case is actually greater than. So it should actually result in the condition is essentially it should be strictly greater than Q, which is not happening here. Like 1 is greater than or equal to 4. If you are okay with if we stick to the relaxed form of dominance, we can kind of consider this particular as well. So 4 also comes over. 4 results in actually incrementing the value of NP to 1. Or if you want to go with a strict dominance rule where you do not entertain the equal to sign, then this will be essentially 0. Now you have to repeat it for other solutions. So now you want to compare it with say you compare 2 with 1, which you essentially don't have to do because you already know what is the relation between 1 and 2. So you do
Yeah.
not do this comparison. You compare 2 and 3. We will see if you compare 2 and 3, this is greater and this is less than this. So there exists no relation between 2 and 3. Like you cannot say which one of them is what. So 2 and 3, there exists no relation. And then you compare 2 and 4. Is less. And this is greater. This is also same. 2 and 4, you do not have anything. So if it is 1 is less than 2, so when you are comparing it, it should go into SP. So 1 will come over here. And your NP, you do not have any increment, so NP will be 0. Now when you are with 3, you are again 3 you already compared with 2 and you know the solution is like you do not have anything. So you essentially compare with only 4. When you want to compare 3 and 4, this is the particular case where you do not have any relation between 3 and 4. So which again is like 3 and 2 also doesn't have any relation, and so which means SP will be 5. 5 is essentially your empty set, and NP is also you do not have any relation, so NP will remain 0. Now when you come to the last case of 4, you don't have to compare. You already compared with 1. The relation, okay, I have erased it. Fine. When you compared 4 with 2, you don't have a relation. Yeah, when you compare 1 and 4, which we have done previously.
Yeah.
We kind of told this is less than or equal to, and we are dealing with only strict dominance. So we are not kind of including it in any one of these. So that will also be 0. So now you have kind of obtained all the solutions with NP equal to 0, which means all these solutions are having rank 1.
Okay.
Okay, for this particular example, it turned out that it is not, okay. If suppose you do not have these solutions with and same value of NP, then we need to iterate it for the next loop. I think we are running out of time. Maybe we'll take it up in the next week. We will start with the same example and we'll kind of maybe I'll change the values of F1 and we will see what happens if NP is not equal to G. You can actually come up with values where this
Yeah.
one of them can be 1. Say suppose if you kind
Okay.
of deal with not a strict one, then it can happen like this is 1, 0, 0 and 1. If it happens to be that particular case, only these two solutions will go into the first rank.
Oh, yeah.
And then we have to do another loop. That will be the stage 2 of the algorithm. We will discuss in the next week how to actually do that.
Okay, sir.
Okay. Thank you.
Thank you.